Hey everybody, this is an intro to the Quantopian lecture series. It's mainly intended for people who are less familiar, so if you're familiar with Quantopian and the lecture series, feel free to skip ahead. Quantopian is a crowdsourced investment firm. Our goal is to democratize quantitative finance and level Wall Street's playing field, and do that by providing lots of free tools and data of the same quality that you would get if you were working as a professional on Wall Street. Our business model is to provide capital allocations to the best algorithms that have been developed on the platform. Towards this end, we've developed a lot of educational materials because we want users on the platform to be well educated. The Quantopian lectures have been developed in collaboration with and are used for teaching by many professors at top universities around the world. We also work with industry practitioners to make sure everything is applicable and keeps up with whatever people are working on at the moment. In general, we try to teach theory and intuition through hands-on applications so that you have the code ready to go once you've learned a concept. So without further ado, let's see what's on deck today. So what we're going to be going over today is plotting data. So I'm here on quantopian.com/lectures, and we're going to go ahead and get the notebook. As you can see, there is no video icon next to the notebook. That's because the video is being recorded right now. Hopefully we'll have a video icon there soon. So in quantitative finance, and generally in most quantitative fields, you want to have some ability to graphically represent data because humans are very visual creatures, and we oftentimes want to look for patterns or, see representations of patterns that might exist. Now, this can actually be kind of difficult. And the reason why is as follows, because for anybody who's looked at clouds before and tried to find shapes in clouds, you'll know that humans are generally pretty good at reading patterns into randomness. So you're kind of good at seeing things that you want to be there even when they're not. And this is just a quirk of how our visual processing systems have developed. The result, though, is that it's actually kind of dangerous to use plots to try to convince yourself that you're right. And so in practice, oftentimes, I think you do want to end up doing kind of rigorous, what's known as statistical testing and developing p-values and confidence intervals on top of what you're doing. So plots can kind of be misleading sometimes. Like it's very easy to, draw some meaning out of a plot that doesn't really show a relationship at all. So that's just something to be careful about. In general, I like to use plots as a way to check if I'm wrong. And that's something we'll talk about more in the lecture series later. But generally this notion that, you'll come up with an idea, and then in statistics, your ideas are now your worst enemies, right? Because you're trying to convince yourself that they're wrong. And then the idea is that only the ideas that survive this trial by fire, only the ideas that you kind of have failed to break are the ones that are good ideas, that are good hypotheses. And it's the same thing here. Kind of use graphs to try to look for reasons why ideas may be wrong, more so than trying to convince yourself that your ideas may be right. But obviously, this is not always necessarily the best. You can't be perfect all the time, and it's just something to keep in mind that you don't necessarily trust implicitly information that you see presented in graphs. So they're useful, as it says here. Plots are more useful when you're kind of exploring an idea, when you're developing an idea, not when you're trying to decide if an idea is good. So graphs are a really good way to look for patterns that you may want to definitively test later, but they're really more for exploring, right? They're not for kind of saying, yes, I am right, or no, I am not right. That said, I apologize for taking all this time to rant about statistical testing, although it's very important. Let's just go ahead and get started. So the first thing we're going to do here is we're going to import some libraries as usual. One of the things is this is fairly early in the lecture series, so I'll explain this little piece of code here and this little piece of code. What this does is it's just known as an alias. So this piece of code allows you to import NumPy as NP. And what that means is that you literally just have to type NP every time rather than typing out the full NumPy. In this case, it's only saving you 3 characters, but you can see here that it can start saving you a lot more characters as you import more complicated libraries. Just as a result of how this looks, I'll show you an example. So let's say that you were writing some code here, and you made a new cell, and you wanted to import another library, in this case like pandas, well, you can import pandas, but then every time you want to use pandas, you'd have to type out pandas dot something and then, type out the full thing. Importing pandas as PD, which is much more common, now allows you to type out only PD, and you'll get access to everything in pandas. I'm using the tab autocomplete syntax that we learned in the first lecture here. So we'll close that. And now that we've closed that, let me just start with the first step, which is that we need some data to plot. So in this case, we're going to use Apple and Microsoft in our examples, just because they're kind of two easy stocks that everybody knows about. And we'll use Quantopian's get pricing API in this case. Get pricing allows you to get pricing data for single instruments or a list of instruments. And you can specify fields such as do you want open, high, low, close, or price? What frequency do you want? And then what date range you want. In this case, we're interested in 1 year's of data, 1 year's worth of data, and it defaults to daily frequency if we don't specify anything else. So let's run this cell again. Ideally, we'll get the same code. Yep, the same data. And you can see if we specified, say, another year, it would look different. And so there you have it right there. There's another year. Now, what you can see here is these series can sometimes be a little misleading because in this case, I believe it looks like Apple went through what's known as a split, in which a stock's value becomes too much. And so you kind of readjust the value of that stock, kind of divide it by another number. In this case, you can see it actually dropped in value from hundreds of dollars to less than $100. What that means is that it just means that per share, the stock is worth less, but it doesn't really affect the shareholders, but it can really screw up your quantitative analysis unless you're taking that into account. So that's something that we'll talk about more later, but it's just something to note is that oftentimes, the quality of your data is the most important thing whenever you're doing anything, because if you have garbage data or some problem in your data, you're going to get garbage out. So garbage in, garbage out. Let's try to make sure we don't have any garbage in. Quantopian does a lot of cleaning of the data for you, so this should be pretty good. But you do still have to worry about problems such as splits and that kind of stuff. So the next thing we're going to do is we're going to do a little bit of a trick. Don't worry too much about this. This is just going to change the title of the columns in our data frame here. The columns were objects, Python objects, which we learned about in the Python lecture. But now we're just going to make them into strings. That's all this is doing. It's just a little bit of Python trickery to make them into strings so that we can easily access them. Then we're going to look at the first 5 prices, in this case for Microsoft. That's what it looks like. We could also look at the last 5, and they'd be different. But of course, the reason that we want to plot stuff is so that we don't just have to look at small groups of numbers at once. We want to look at larger swaths. So here's the first thing we're going to produce. We're going to produce a histogram. A histogram is a really important plot in statistics. And there's lots of materials online talking about what a histogram is. We're not going to necessarily try to explain a histogram too much right now, but just bear in mind that it basically, what it does is it tells you how frequent certain observations are. So I could look and I could say, well, observations around 40 are more common historically than observations around 36. So it is more likely that the price was 40 than it was 36. This basically just says historically, over the period of time we looked at, what is, the distribution of prices. That's all it's saying. And this is basically kind of an empirical estimation of what would be known as the probability density function, which is kind of like saying for each price, how likely is that price to occur? And, obviously we don't ever know that perfectly, but we can try to estimate it by looking at historically what's happened. For reasons of non-stationarity, which is something we'll discuss in later lectures, this doesn't always work very well, but it's a good way to look at your data. The next thing we're going to do is we're going to actually look at the returns of Microsoft plotted in distribution. And this is actually much more interesting. So you can see here the code we're actually using to do that is plt.hist, so that's the actual function that makes the histogram. And again, just using your question mark syntax, you can go ahead and see what the arguments are. See, I hadn't run that cell up before, and so that's why I couldn't get at the contents of PLT. I was too distracted in trying to explain the aliasing syntax. But if you look at plt.hist, you can use your question mark notation, and it will tell you all sorts of really interesting information about this function and what you can do with it. We're just going to focus on this little example, which is just we feed in Microsoft's data, and we say we want 20 bins. The bins just define how many of these columns you're going to see. You can think of it as the resolution of the plot. So if we knock that down to 5 bins, it would look like this. And if we knock that up to 100 bins, well, I don't think we even have 100 data points, but it would look kind of silly, right? It would look like this. So we're going to go back to 20. And then the next thing is you just say, well, plot the X label, and that's going to be price. Plot the Y label, number of days observed, and plot the title. It's pretty simple. And then the last thing we do is we just squelch this line output at the end. And if we don't do that, we get this weird plot object that's returned that it tries to print out. This is Python trying to print out the plot object because plt.title actually returns like an object that's useful in some cases, but we're not going to worry about it now. So we just kind of ignore that using this semicolon syntax, and that makes it look nice and clean. And again, we just do the exact same thing for the returns. And we see this distribution. And so you can see the returns distribution starting to look more useful, right? This price distribution, it looks kind of random. And we discuss why that is in the orders of integration and non-stationarity lecture that's later in the series. But basically just understand that oftentimes returns distributions, and again, we're computing returns here as just the day-over-day change in our pricing data. Returns distributions are oftentimes more useful for these cases. Here's another one. This is cumulative histogram, or a discrete estimated cumulative density function for those of you who are more familiar with probability and statistics. If you're not, don't worry. We have plenty more discussion of that in later lectures. But a cumulative histogram just looks at, rather than looking at the distribution like this, it says for each return value, what's the chance what is the chance, rather than that I get precisely that return value, but what is the chance that I get something lower than that return value? So that's why it's cumulative, right? So when you get to 0, you're saying not what is the chance that I see a 0% return, but you're saying what is the chance that I see anything less than a 0% return? And that can be useful for some cases, such as when you're trying to compute the chance that you get a certain loss. And so you can see there's, an strictly increasing chance that you observe anything up to the fact that you get your maximum at the maximum value that we saw over that time period, which is a 4% return. And I want to point out that these things are not the same all the time. If we change the year, then we're going to get different outcomes in different plots, because the distribution of returns is going to change. So here is it for 2014 to 2015, and here is it from 2013 to 2014. Way different. You can see there. You even have like a 10% loss on one of the days. And the cumulative distribution is also going to look different. You can see there. So it's just something to keep in mind that, don't look at these plots. Again, don't look at these plots and try to convince yourself you're right. Don't look at these plots and say, oh, well, clearly the chance of having a less than 4% return on Microsoft is 0%. That would be a very naive way to look at these plots. All this is saying is that over the time period you're analyzing, there was this many observations of this magnitude. And not necessarily that will continue to be the case into the future. So that's just something to keep in mind. Here's another really useful plot. This is a scatter plot. This is a very useful plot when trying to visualize how two data sets are interacting with each other. And in this case, we're looking at the interaction of the prices. And you can see on the x-axis, we have Microsoft price, and on the y-axis, we have Apple's price. And what each point is saying is a day. So on this day, Apple's price was just shy of 100, and Microsoft's price was maybe $47. That's what happened on this day. On this day, Apple's price was $92, and Microsoft's price was $40, $41, somewhere in that range. So basically what this is telling us is if structure starts emerging in this plot, and if it's not just random points scattered over the XY plane, then we have, maybe some indication that we should go look for interesting relationships. Because, in this case, what are we saying here? Well, what looks like what's happening here is that it seems like they tend to move up and down somewhat together. In that on days when Apple is high, Microsoft is also likely to be high, right? You don't see many points where Apple is high, right? So you up on the y-axis, but Microsoft is low, right? So in fact, if Apple is $100, the Microsoft here, there are no points where Microsoft is less than $44 when Apple is over $100, right? That's kind of the intersection here. So what this is saying is that they tend to move together. And you'll find this is true for most pricing series. And the reason why is that the market tends to move together. Because, when the market goes up, most stocks go up. When the market goes down, most stocks go down. So I think that's most likely what we're seeing here, although you might also be witnessing some effects of, they're both computer companies that probably will move together when demand for computers are high versus when demand for computers are low. So that's just something that can kind of come out of here that's interesting. And we'll also look at the returns. But again, this is just plt.scatter. Pretty simple. You just put in your data points for your X data and your Y data. Same X label, Y label title syntax. And you can use the question mark notation to get more information on scatter, or you can look it up online. There's lots of documentation available. Here's the returns distribution. Much less structure in there. Would be much harder to argue that any kind of relationship exists here. And again, you wouldn't look at this and be like, haha, a relationship definitely exists. You'd look at this and be like, maybe this merits further exploration and investigation, right? You don't want to use plots to try to convince yourself you're right. Let's look at a line plot. So this is a line graph. And in this case, we're actually going to do two lines. One line is the Microsoft data. One line is the Apple data. And in this case, we're just plotting them so we can see them together. And the x-axis is the date range. And it knows to do this automatically when you feed in a series. And if you look at what we actually give it when we feed in Microsoft, well, that's a series, right? There's dates, and each date has a corresponding price. And we can check this if we do Python type. So this is just a global function in Python. It is a pandas series. And the plot function knows what to do with that. You can also manually feed in X and Y data to plot. So if I did plt.plot and I fed in X data of 0, 1, 2, and I fed in Y data of 0, 2, 4, I'd see this, right? This is just interpolating a y equals 2x curve. And you can put in any value you want for this, and it will show you what that line looks like. So just keep in mind that you can feed in the X and Y values raw, or you can also feed in a series in which it will kind of know to make the X-axis the dates. And then the only extra thing we're adding here is now a legend, and a legend is just an array with a list of labels that we're going to apply to each of the different things that we're plotting. So in this case, it's just going to go in order. So we've plotted Microsoft, we've plotted Apple, and then we've plotted the legend, and it knows to apply the labels correctly. And then the last thing we're going to do here is plot the returns of Microsoft as a line plot. And again, you can see here, well, what we're looking at here is just kind of doesn't look like much of anything, right? It's kind of a lot of randomness here. There's some spikes. This is an example of, there's lots of different types of structure, and different plots are going to get at this better. So, is this plot that useful for looking at what's going on? Probably not as useful as looking at something like this, right? So develop more and more plots, develop more and more ways to understand data, and really try to explore data and really understand what's going on. But also don't use plots as a way to test data. Always use rigorous techniques like out-of-sample testing, which is something we'll talk about later in the series. And most importantly, never assume conditions hold. Don't ever look at a historical period of time and assume that the conditions shown in a plot will continue to be true in the future. This is kind of the biggest fallacy of forecasting, is that people just look at the past and they assume that the past is representative of the future. And it can be very easy to make that assumption implicitly when you're looking at a graph, right? That's like I said earlier, when you look at this plot and you're like, oh, well, it looks like the chance of Microsoft going below, having a negative 4% return on one day is very low, so I'm not going to worry about it. But I showed you that if you look 2 years back, that actually happens. So the distributions change over time, and what you want to do is apply much more rigorous statistical methodology to trying to figure out what forecasts make sense and what things are consistent and what things are inconsistent. And, that comes much later in the lecture series. But just keep in mind right now that, in general, don't look at historical time periods and assume that they reflect the future. That said, plots are cool. You can use plots to do lots of stuff. There's lots of more complicated plots you can use. There's the Seaborn library that you can use to do lots of fancy plots, and there's full documentation for that online if you look up Seaborn, Seaborn, and you can import it and use it in here, and it's used in some of the other lectures. But you'll see more and more plots as you go along through the lecture series, and I just wanted to give you the tools to do a few simple plotting techniques within Python notebooks. Hey everybody, thanks for watching another Quantopian lecture video. I just wanted to say that all the lectures are always freely available at quantopian.com/lectures. We also hold workshops around the world. Information on those can be found at quantopian.com/workshops. We work with local experts to bring you full-day interactive hands-on approaches to learning this stuff and try to focus more on giving you the tools so that you can leave the workshop able to learn more on your own than trying to cover any specific technique. For information on events near you, you can check our events page, also linked from here, and see if there are events coming up nearby that you might be interested in. This also includes meetups and hackathons and all sorts of stuff in addition that we do to try to make education more accessible. Lastly, if there's anything that confused you today, or if you want to start a discussion on the stuff that you learned, please head over to the community forums available under Community Forums in the menu bar. Post a question, look for other similar questions. In general, it's there to really give you more tools to keep moving forward and not get stuck and continue using the knowledge that you learned in the lecture series. So again, thanks for listening, and hopefully I'll see you again soon.